Hello everybody, welcome back to another video. Today we're going to be going over one of the most important algorithms in machine learning, that is linear regression, and we're going to do it from scratch with no external libraries like scikit-learn, only Numpy for the math involved in gradient descent, and I'll get involved in all the theoretical ideas involved in linear regression in just a minute. Stick around for the entire video. Let's get right into it. So we need to import three libraries. The first one is obviously Numpy. And then there are two libraries that we're going to be using for the data processing. That will be pandas, and we're going to be using matplotlib. We only really need pyplot today, so that's why I'm doing it like that. Alright, so we need to ask ourselves like what data we're actually going to be using. So I'm in Kaggle right now, so I'm going to go to the add data section. And the data set I'm looking for is a data set that is salary versus years of experience. So let me open the CSV file so you guys can see exactly what I'm talking about. You guys see here, years of experience, salary. If you guys can't see that, let me expand that for you. Now you can see we have 30 data points in this data set, years of experiences versus salary. Okay, so this is the data we're going to be using today. So the first thing you do when you import data is you need to use pandas to read the CSV. The way we do this is pretty self-explanatory. pd.read CSV, and then we need to copy the file path. So if we just go over here, Kaggle makes it really easy for us. We just copy that file path. All right, and then we need to put that in quotes, single quotes, double quotes, whatever you prefer. And in other IDEs, it might be a little bit different where you'll actually have to go to the file path and copy it manually in your like File Explorer or whatever OS you're using. You'll have to copy the file, but in Kaggle, it's super easy. And we want to get some insights on our data, what it looks like. We already know what it looks like, but usually you'll just use data.head to know how many columns you have, how many data points, like the first look at what the first couple data points look like. So we run that and the draft session is starting. So in a minute we'll see exactly what this outputs. Basically this is just going to give us a quick summary about the data, and here it is. Okay, so we have our first 5 data points, years of experience versus salary. Alright, so now what we're going to do is we actually need to define X and Y. So we have 2 columns, so years of experience is going to be our X and salary is going to be our Y. Usually the time variable, the variable that is correlated with time, is the X variable. So what we're going to do is it's like this. We're going to say X equals data, which is our actual CSV. And then we're going to call on this column, years experience. Oops, years experience, okay? And then the same for Y, but now we're going to use a different column. We're going to use the salary column. So now that we have that, let's see what our data actually looks like. So we'll do plt.scatter X, Y, and we'll be able to see what our data looks like. So this is our data. And if you want to, label it, you could say plot.title, years, well, it's salary because it's Y versus X, salary versus years of experience. Oops. Let me just do plot.show. Okay. So this is, this is what our data looks like. We need to draw a general line that will go through the data. So let's say I have 6 years of experience. I'll be able to predict to a certain degree what salary that will yield. All right, so now the question is, we have our data. How are we going to make a line of best fit? Now remember, I'll write it right here. We know that in math, we have the equation of a line y equals mx plus b. All right, that's something that's known. All right, That's a mathematical equation that's known. That's the way we approximate a line. Now, if you ask someone on the street, hey, approximate M and B for this data that we're looking at right now, they probably wouldn't be able to get what the M and B values are. There would be a pretty huge delta, pretty huge difference between the predicted output using the equation they came up with, using the M and B values they came up with, and the actual output of the data. So really the goal is minimize the difference of our prediction and the actual output, okay? So we need M and B values that we don't know to best approximate a line that cuts through the data that will be able to allow us to predict for a given year of experience a salary. How do we do this? We start with random M and B values. And basically what we do is we say, okay, here's a prediction. And we use this equation called mean squared error, which tells us the amount of error between our prediction and the actual output. Yi is the actual output, and y with the tilde on it is our predicted output. Okay? So it's 1 over n, the amount of samples, and it's finding the difference between the actual y and predicted y. We square that difference and then find the mean of the squares for every value in our data set. All right, so that's what mean squared error does. Finds the difference between the actual y and predicted y, squares the difference, and then finds the mean of squares for every value in our data set again. All right, it's really important for you guys to grasp mean squared error. That is, again, the way we measure the error between the predicted and the actual output. Okay. Now, the goal of gradient descent, which is the algorithm that's going to help us draw a line exactly where we need it, the goal of gradient descent is to minimize the error that is outputted by the mean squared error equation. It's trying to minimize that error. It's trying to find M and B values that are exactly right so that the error is extremely small. How does that happen? Okay. So imagine M and B, let's classify them as weights, all right? Let's call them weights. Now imagine for different weight values, there's a cost or an error associated with those weight values, okay? As you see in the parabola, or the, kind of squared function that you see. This is like a two-dimensional way of visualizing the error for different values of M and B. Let's individually look at one of those weights. So we start with this initial weight. We first take the derivative of our cost function or of our error function to understand what direction should the weight get smaller or larger, what direction should the weight go to minimize the error, because we're trying to get the weight to a point where it's the exact right value so there's little to no error. And that's the minimum cost, as you see on the bottom of the parabola. So we take that derivative to know exactly what direction we're going in, and in this case we're going downhill. All right, we're going towards the middle, and that's what the gradient is for, to understand what direction we're going in. That's just the derivative of the weight at a given point. All right, so now we're going downhill, and our values, our M and B values, are going to be updated in a certain way to reflect us going downhill. All right, these values are going to be updated because we want the values to be updated for the error to be smaller. Okay, so the way a value is updated is as follows. We have our M value, so let's say M is 3, okay? And we're going downhill. We want it to get smaller because, as you can see here, the weight is getting smaller. So the way we update a weight is as follows. The value of the weight currently minus, and these are really important concepts, so just bear with me here, the learning rate multiplied by the gradient. Okay? The learning rate multiplied by the gradient. Alright. Learning rate. What is the learning rate? You guys see the little arrows here? Those little arrows indicate how large of steps the weight is taking towards the minimum cost, the minimum error. How large of movements it's making towards that error. Alright, towards that minimum error. It's really important to set a certain learning rate so that the weight doesn't jump around and that it goes exactly in small incremental steps to that minimum cost. Okay? So the learning rate is the size of the step. Imagine it as the size of a shoe. How much are you going to step towards that minimum cost? The gradient is the direction, as we said, the derivative at a specific point where the weight exists. Alright, so just that tangent line. Okay? That's how we update our weights. Now, the only thing left is to actually implement this in code. So let's go through step by step. Just to review what we've done so far, all we've done is imported our data. I'm going to delete this because it's going to cause us an error. And we graphed our data. All right, now here comes the nitty gritty. Here's where we actually want to start actually writing the code. So we define m as 0 and b as 0. Remember from the equation y equals mx plus b. I'll write it here really quickly for you. All right, now a couple of other important things. We want to define our learning rate. I'll call it learning rate. I'm gonna make the variables very long so you guys understand exactly what I'm talking about. We're gonna make that 0.01. This is just an accepted value. You can play with the learning rate, but it will also skew your data. Or skew the line of best fit. So let's start with 0.01. That's an accepted number. All right, and the amount of epochs, we're gonna say for now 5,000 epochs. This is the amount of iteration. It's just going to be the amount of times the algorithm runs to optimize the line of best fit. And we can play with this around if we don't get a result we like. And I probably will in a few minutes. Okay, now for gradient descent, we need a list called loss or error. Okay. We'll call it loss. We'll actually call it error. I'm being very indecisive. And this is going to tell us our error over time. And this is usually called loss, but we're going to call it error just for you guys to understand easier. This is going to minimize over time. We're trying to minimize the error, right? So ideally, we'll see a graph that kind of is shaped like a hockey stick. All right. And the last thing we need to do is create a float that tells us the amount of data points we have. I'll expand on what this actually means in a minute. All right. Okay, so now the actual algorithm. So for I in range, epochs. All right, this is going to iterate through the amount of epochs we have. So in our case, it's 5,000. All right. Now we have our prediction. So our prediction is going to be the same structure as y equals mx plus b. We'll call it y hat because of this little hat. We'll call our prediction output y hat, and we'll set that equal to m times x plus b. All right, let me just go like this. All right, m times x plus b. All right, that's our prediction output. All right, that's just a line. Now we need to define our equation for mean squared error. Remember, this is what mean squared error looks like. I'm going to show you exactly how I write it. It's exactly what the equation looks like. 1 divided by n times np dot sub y minus y hat, because y hat is our prediction, squared. That's it. All right. Let's review MSC one more time. 1 over n, sum of y minus y hat squared, square of difference between actual and predicted. It's exactly what we wrote here. Okay? And then we're going to append MSE. All right, so we're actually making a prediction, comparing it to our y value for a given y, and then appending our error, okay? So we're actually going through the process of making a prediction, comparing it to the actual output, getting the error, appending that error to a list, and we're gonna plot that list in a minute. All right, now we need the derivative. All right, we need the derivative, the gradient for each of our variables. So we need the derivative of m, and we need the derivative of b. Okay? If you guys don't know what derivatives are, I encourage you to go on YouTube, some other place where people teach math, and I bet there are a bunch of videos explaining how to take derivatives. But in short, we're taking the partial derivatives with respect to m and with respect to b. And with those partial derivatives, the output is as follows. Negative 2 over n times the sum of x times y minus y hat. Let me put this underscore here. Y minus y hat. Okay. And that is that for the derivative of m. Let me make this derivative m, derivative b, okay? And the same thing here, but with respect to b, the sum of y minus y hat, okay? Those are the derivatives. And then, as we said, we need to update our values. M equals m minus learning rate. If you guys have any questions, by the way, 100% feel free to search them, say them down below. I'd love to answer any of your questions, 100%. I'm here, always on YouTube, ready to answer your questions. Feel free. The learning rate multiplied by the derivative. And the same for b. B minus the learning rate multiplied by the derivative. Our algorithm is done. Congratulations, we're almost there. Alright, so the work for the algorithm is actually done. The last thing we actually have to do is just visualize our work. Alright, so let's get out of this for loop. Alright, and we need to do two things. So we actually need to use np.linespace, and we're going to use this because a lot of times with regression or just dealing with data a lot, you're going to have issues with equally spaced lists, gaps within the data. So what we need to do is create two lines, an x line and a y line. Our x line is equal to np.linespace. And our y line is equal to our m value times our x line plus b. Alright, our x line is basically taking our data and plugging it in, multiplying by b, adding b, multiplying by m, adding b. Alright, so now all we have to do is literally just plot our line of best fit. Okay. This is our line of best fit. And now let's see how good we did. So our plot title will be the same as our initial plot title. So let's just take that. We'll just copy the entire thing and plot.show. Oops, I almost deleted that. Plot.show. All right, so boom. All right. Now we actually need to plot our scatter plot, x and y. Before we do that, we want to plot our line of best fit. So we're going to say x line, y line. You see if you only plot one of these, it's going to cause an error. And it's just your line of best fit won't actually fit the data. And so that's all we have to do. And if we want to label the X and Y, we can do that in a minute, but I just want to show you guys the result of your work because we've been waiting so long. And let's actually also plot our loss. All right, so we're just gonna plot our error list, okay, and plot.show. We only need that once, so let's take that away from here. Let's run everything and see how it goes. All right, so let's rerun this. If we have any errors, we'll go back and check them out. All right, plot X, Y, X line. I'm just checking really quick. We have everything right. We have an error. Y, oh, I forgot to put an underscore. Line 17, derivative B. Ah, forgot to put an underscore here. All right, here we go. We have our data with our line of best fit, and we have our loss graph. And as you can see, the loss is reduced over time pretty dramatically. And I would say that line of best fit is optimized almost perfectly. We can see that even some of the predictions are exactly on the line. So give yourself a pat on the back. That was amazing. Thank you guys so much for watching. If you have any questions, make sure to leave them right down below. Anything I didn't cover, I didn't answer. I hope you guys got some insight from this video and had fun making a linear regression model from scratch just with Numpy and pandas and matplotlib. I'll see you guys in the next video. Peace.